Let's talk about the Klein Gordon equation. The Klein Gordon equation is a relativistic wave equation. What that means is that it's a wave equation for particles moving at relativistic speeds, that is, the speed that are greater than the speed of light. It is also related to the very famous Schrodinger's wave equation. The Klein Gordon equation is second order in space-time and is Lorentz covariant. What that means is that it can be written in terms of Lorentz covariant quantities, that are the quantities that remain unchanged under the Lorentz transformation. That is to say that if they hold in one particular inertial frame, then they shall hold in all inertial frames. Now, it is also important to note that the solutions of such equation include a quantum scalar field whose quanta are spin-less particles. That is, they are spin-zero particles. Now, before we move on in deriving the Klein Gordon wave equation, I'm going to be using natural units that I'm going to be setting my h bar equal to c equal to 1. Also, let's recall some of the things that we know that our Schrödinger wave equation, again with my h bar and c equal to 1, is written as iota partial time derivative of my psi plus 1 over 2m del squared psi plus v times psi is equal to 0. Right. And we also know that when my Hamiltonian acts on my psi, it gives me a constant energy eigenvalue times psi, and that my Hamiltonian can be written as the sum of my kinetic and potential energy. Right. Now, when we move from classical to quantum, we do that by the notion of operators, and we quantize our observables, quantize our quantities. That is, in this case, we are going to quantize energy and momentum. So the energy operator is defined as iota and partial time derivative, and my momentum operator is defined as, or is represented as, negative iota gradient operator. Alright, now to move on and to derive the Klein Gordon wave equation, I will not be using my Schrödinger's wave equation, but instead I will be using my famous Einstein's energy momentum relation. That is, my E squared, energy squared, is equal to m squared plus p squared. Again, note that I'm using natural units here, and that's why my c does not appear in the equation. Now, from here, we're going to simply quantize this equation or this relation by putting the operator value of E and of the momentum. And I know that my E from last slide is represented as iota partial over partial t, and my momentum is represented as negative iota gradient, right? So I just have to square both of these quantities and put them back in my equation 1, let's call it. Alright, let's do that. When we do that, what do we get? We get negative iota square negative partial square over partial t squared. And now this will act not on a wave function but on some scalar field that I'll call phi. And that is because we're talking about relativistic quantum mechanics. Now, all of this will be equal to my m squared plus the quantized value of momentum squared, which will be again negative gradient squared, and then all of this times some scalar field phi. And let's write this down a bit neatly. It will be negative partial squared over partial t squared phi is equal to m squared phi minus del squared phi. And well, basically this is my Klein Gordon wave equation. But we are talking about relativistic quantum mechanics, and therefore we shall switch to a 4-vector notation. And to do that, let's start with what is a 4-vector. Well, let me write this down first. We have Ct prime z prime is equal to a transformation matrix that is cos hyperbolic theta minus sine hyperbolic theta minus sine hyperbolic theta and cos hyperbolic theta. All of this matrix acts on Ct and Z. Right? Now, any set of 4 quantities that transform as such is called a 4-vector. So, let's say that we have some x contravariant will be then written as x superscript 0. This is for the time component of my x, and all the spatial components will be written as some x and tilde. So x tilde includes all of the spatial components. Now let's also move further and define a quantity called the 4 gradient. So I'm going to write it 4 grad. And 4 gradient is defined as partial covariant partial mu is equal to partial over partial t, again the time component, and the spatial component I'll write it down as del vector. Right? Alright. Now let's take a dot product of this 4 gradient with itself, and to do that, to do a dot product, we need to call upon the metric, and the metric is G mu nu in superscript, and I'll be using the convention of plus minus minus minus. Alright, so now how do we write this dot product? Well, to write the dot product, we say we contract these two. Partial mu is written as equal to G mu nu partial mu partial nu. Right? Okay. Now let me write down my matrix of G mu nu. So G mu nu is represented with a matrix that is, as I said, I'll be using my plus minus 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 convention. So I'll have 1 over here, minus 1, and minus 1. And all of the other quantities are going to be 0. Now this is a bit long and lengthy, so I can write this as 1, 0, 0 and -1 with the tilde, where -1 tilde is distributed over all of the spatial components. Alright, now what is the next step? In next step, I'm going to move this g mu nu in between these two operators, and then I'm going to write that in the matrix form. So let's do that over here. So partial mu is equal to the matrix form of my partial mu is partial over partial t and gradient over here. Then I have my metric, and that is, as I wrote up here, is 1, 0, 0, -1 tilde, and then I have partial over partial t and my gradient operator over here. Alright, so the next step is very obvious. I'm going to multiply out these two matrices, and what I'll get is that my partial mu is equal to, after I multiply out those two matrices, I get partial over partial t in a matrix gradient times my partial over partial t, and because of that multiplication this becomes negative gradient. Alright, now let's just multiply these two out, and finally we will get partial mu being equal to partial square over partial t squared minus Laplacian, right? Minus my gradient square. Alright, now this thing over here will be very useful, and I'll further go on to define my partial mu as an operator that I'm going to represent it like this, and this operator over here is called the D'Alembert operator, this operator over here, right? Okay, so now I can write this, that my D'Alembert operator is equal to partial square over partial t square minus my Laplace, right? Okay, now if you recall, I think I'll do it over here. If you recall that we had already derived our Klein Gordon equation that we said earlier, and it was as such: negative partial square phi over partial t squared was equal to my m squared phi minus my Laplacian of phi, right? It's getting a bit congested over here, so let's move on to another page from this step. And now all I'm going to do is play around with this equation and move the terms here and there, and then that will give me partial squared phi over partial t squared minus my Laplacian of phi plus m squared phi. All of this is equal to 0. Alright, now if you remember how we defined our D'Alembert operator, it was D'Alembert is equal to partial squared over partial t squared minus gradient square. So if you remember this, you can write this equation over here as following: the Lambert of phi plus m squared phi is equal to 0. And this over here is our Klein Gordon equation, and it can further be represented as the Lambert plus m squared phi is equal to 0. And this over here is our Klein Gordon wave equation. And this is invariant under a Lorentz transformation. That is, it is a covariant wave equation. And that is because we started with a 4-vector formalism, and that implies that this equation over here is indeed a covariant wave equation. Now, note that this wave equation is extremely limited, as it is only applicable to spin 0 particles. One of the very famous particle is the Higgs boson. The Higgs boson. And the Higgs boson is a spinless particle. That is, that the spin is 0. So it is a spin 0 particle. And this Klein Gordon wave equation is applicable to the Higgs boson. It is very limited. However, this was the first attempt at relativistic quantum mechanics. So that's it for this video. I hope you enjoyed and you got a brief idea of what the Klein Gordon wave equation is and how do you derive it.